Alright, there is nothing better right now, so we'll just try to use this one. Alright, so how do we generate the Routh table? What we do is, so we write this down. You see this, the polynomial, right? You write the order of the polynomial on the left-hand side, and then what you do is, you populate this with the coefficients. So you have 1, 31, and then you have 10, 1, 0, 3, 0. Okay. So what you do is, all the odd coefficients are in the first row, and the even coefficients are in the second row. Okay. This will always be true regardless of what order polynomial you are dealing with. Okay. So only the first two rows are always populated. The first row is always odd coefficients, and the second row is always even coefficients. So the odd coefficients here are 1 and 31, and the even coefficients are 10 and 1, 0, 3, 0. Now, what you do is you start this cell. So think about it as like this. This is a table, right? What will a table have? A table will have rows and columns. Right? So what you're looking at here is rows and columns, and you need to populate each of these cells, each of the rows and columns. Okay. So now this one is the product of these two minus this over this element. Okay. So it is 1030 minus 310 over S1, or let's call this cell 3, 1 is equal to cell 1, 1 into cell 2, 2 minus cell 1, 2 into cell 2, 1 over cell 2, 1. This is always the pattern. Okay. This minus this over this. So if you do it, this cell, for this cell it will be these two minus these two over this, or over this. Sorry. So this cell would be these two minus these two over this. There's nothing here, right? So you don't have to worry about that. So what is this? This is 1030 minus 310 over 10. Okay, so this would be 772, right? Now this would be again, see this would be these two minus these two over this. Get it? This is 0. These are considered zeros. So it will be 0. Alright. This would be again this minus this over this. Okay? So this would be minus 1, 0, 3, 0. This would be. Is it clear, this Routh table, constructing Routh table? This is very simple, and try to get it. Even if you don't get what has been done until now, it's independent. So if you're thinking about scoring or doing well in your exams assignment, this is a very simple technique. All you need to do is you start with this. Okay, you are given this. First, you need to determine the closed loop transfer function, right? Which is, for a unity feedback system, what is it? It is GS over 1 plus GSHS. That is always the case, okay? So HS is 1, so you end up with this. You take this, you look at the denominator, the polynomial in the denominator. And what is the order of this polynomial? Third order polynomial. So what you do is, you start with the polynomial here. So if it is third order, you start with S cube, S square, S1, S0. You always pre-populate the first and second row. Sami, you're not going to get it and you're going to struggle. I'm trying to help you pass the course. I'm repeating it because you were again, when I was doing it, you were on your cell phone. I am repeating for you especially. Okay. So when you do this, you populate the, is it clear? Is it making sense to you now? Okay. You populate the first row with odd coefficients. So you see the odd coefficients, 1, 31, right? And the second row with even coefficients. And this is always the case. Even if it is a fifth order polynomial, you just do odd coefficients and even coefficients. So you'll have 3 columns then, right? You have 5, 3, 1, right? And 4, 2, 0. And then you start computing the other cells. The way you compute is this minus this over this. This cell would be this minus this over this. And this cell would be this minus this over this. Alright? So you do this. And this is example, if you want to go back and look, this is example 6.1. Page 306. this is, if you look at it, this is the negative of this. Okay, always negative of this. This will be minus 72. This will be minus 72. This is plus. Okay. Now, how do you interpret basic Routh table? Okay. So this is how you interpret number of roots or poles in the right half plane is equal to number of sign changes in the first column. It's that simple. Okay. So number of roots. How many sign changes do you see in the first column? It's 2. So you come like the way you look at the sign changes. From this to this, is there a sign change? From this to this, is there a sign change? So that is 1. From this to this, is there a sign change? There are 2. Okay. So there are 2 poles in the right half plane. Okay. So if you look at this, if you plot the j omega and S plane, all right, there will be this half of the plane will have 2 poles, which means the system is all right. I'll just continue. I don't know how to teach you guys, because any poles in the left half plane or any poles in the right half plane, even if you have 1 pole in the right half plane, the system is unstable. Okay. Poles in the right half plane means system is unstable. Even a single pole or a single root in the right half plane means the system is unstable. Okay. Any pole on the imaginary axis, which is just imaginary, is marginally stable. And if you have all the poles in the left half plane, only then the system is stable. Okay. So if you look at this, if you see that there are 2 poles in the right half plane, this means system is unstable. Any poles in the right half plane means system is unstable. Okay. Any poles, again, try to understand, I'm repeating, any poles in the right half plane means system is unstable. For a system to be stable, all the poles, you see right half plane? So what is right half plane? Huh? Right, this is the imaginary line. Everything on the right side is a right half plane. Everything on the left side is a left half plane. Okay, so all the poles have to be on the right half plane for the system to be stable. What do you mean by that? All the roots of this polynomial have to be in the left half plane. Okay, they have to be negative. If there is a positive root, that is unstable. So if you check, what are the roots of this equation? Let's check this. I'll show you. See that again? Right, it would be unstable. Even if there is one root on the right half plane, the system is unstable. Okay. So I'll show you. So roots of this polynomial, what is the polynomial? You have 1, 1, 10, 31, and 1, 0, 3, 0, right? All right, if you see here, you can observe that there are 2 poles, there are 3 poles or 3 roots for this polynomial, right? So this is the polynomial 1, 10, 31. This is that polynomial 1, 10, 31, 1, 0, 3, 0. So if you just use this equation, this command roots, it will give you the roots. The roots are, is this visible? Better? So are the roots visible? So if you look at where the roots are, how many roots are in the right half plane? Which are the roots in the right half plane? Huh? How will that be on the left hand side? Don't think, Sammy, it is, see, how can you, alright, how do you plot those? This is 0, okay? So you have the first one. Where do you plot the first one? How do you plot the first one? Huh? Negative 13 point, that is a real part, right? There is no imaginary part. So negative means positive is on the right hand side. Negative 13 would be something somewhere here. So look at the next one, 1.7, right? So you have 1.7, this, and on top, right? 1 and bottom. So you see these 2 roots are in the right half plane. And this, try to understand this. There are two roots and there are two sign changes, right? So the sign changes itself will tell you how many roots are in the right half plane. And you can immediately tell whether the system is stable or not. All right? There are two special cases which we might encounter. Okay. So this is the basic Routh table. Okay. When you're constructing the Routh table, you might encounter a special case. Case 1. Only in the first column. Okay. So let's say if this was 0, right? There's a 0 in this cell. What's going to happen is this element would become infinity, because what you're doing is you're doing this minus this over this. Right? So you're dividing by 0 and you get an infinity, and you don't know how to deal with infinity, right? So in that case, what do you do? All right. So we'll take a look at another. So this is the solution to this is called stability via epsilon. Method. Okay. So you take a look at this system, 10 over S5 plus 2 is 4 is 3s cubed. Is 5s plus 3. So you're asked to determine the stability of this system. Okay. The closed loop system. Or let's say, let me do this. Okay. This is given to be your closed loop system. Okay. is not the forward loop, this is the closed loop itself. So where do you start? Right, you start with S5 and S4. So what is, how do you populate this? Right, so what are the numbers? No, I have 1, 3, 5, right? And the next row is? Huh? So we have 1, 3, 5, odd. No, you take a look at this. Odd coefficients. S5 is the odd coefficient. S3 is the odd order. S is the odd. This counts as even. Okay, so you have these, this even. Okay, so you have 2, 6, and 3. Okay, this is where you start. So you have odd and even. S0 is considered as even. Alright, so now you have this. So what do you start doing? You start doing this. Okay? Here, what you're going to end up is, you're going to end up with a 0. Okay? So let me just rewrite this, okay, so that it will be easier for you. Let's say this is A1 or A3, A1, A2, A0, and this is B1, B3, B1, B2, B0. You understand this? I'm just naming these cells. This is cell A3, cell A1, cell A2, cell A0. The reason it was named so, because if you look at this, so what was A3? The polynomial we got was S cube plus 10 S square plus 31 S plus 1030. Okay. So you see, this is A3. This is A1 because 1. So this is A2. This is A0. Okay. So B3 would be A2, A1 minus A3, A0 over A2. So it is this minus this over this. Alright. Initially I told you it is this minus this over this, but it is actually this minus this over this. Okay. So you have, this was, what did we get here? We got this as minus 72. And B2 would be, so what would B2 be? Tell me what B2 be? Right. Huh? Over? No. Over B3. So it's always the cell above it. The division is cell above it. Okay, so if you look at this, it was this, sorry, this minus this over this. A2 over A2. Right? So this would be this minus this over B3. The cell above it. Okay, so this was 1030. So you apply the same thing here. So you have this minus this over this. Okay? So what, this is 2, 3, that's 6. Minus 6, which is 0. Right? Over 2 doesn't matter. Now you go to this one. So what will this one be? Huh? It would be 6 times 5 minus 3 times 3 over 6. Okay? So 6 5s are 30. 21 over 6. Alright? Or 7 over 2. So let's keep it like this. Let's do this 7 over 2. Alright? And this would be 0. Because you don't have anything over here. Alright? Now this is a problem. Alright? A 0 in the first column is always a problem. Because what you're going to encounter is the next one. This would be what? Tell me what is this? This element. If you follow the same pattern. Huh? It will be infinity because you're going to divide by 0. Alright? So what you do in such a case is, you replace this by a very small number called, and call it so I'm just going to move this a little bit to the right, to the left. You replace this by a small number called epsilon. Very small number called epsilon, just to avoid the dividing by 0. So now you're going to get 6 epsilon minus 7 divided by epsilon. Right? So you have 6 epsilon minus 7 divided by epsilon. Alright? What would this be? 3, right? Sorry, yeah, it would be 3, correct? So it's this divided by, minus this over this. So you'll end up with 3. It is just 3 into 7 over 2 over 7 over 2. Right? So you just, the 7 over 2 always cancels. It's end up with this number. This would be 0. Alright? So the next one is this. So you have going to get a little bit complex, but it's not that difficult, okay? So you have six epsilon minus 7 over epsilon into 7 over 2 minus 3 epsilon over 6 epsilon minus 7 over epsilon. You have minus 3 over here, right? So that doesn't go, okay? So let's just keep that. We don't have to worry about. So you have 6 epsilon minus 7 over epsilon over 7 over 2 minus 3 epsilon, the whole thing over 6 epsilon minus 7 over epsilon, okay? Or you can say this is epsilon minus 7 over 2 minus 3 epsilon square over 6 epsilon minus 7. We'll use that, okay? If you simplify, you're going to get that. All right. What is this element? Zero. What is this element? Zero. All right. What is this element? It's 3. See, whenever you encounter a 0 here, so what is this? This into this over this, right? So this whole thing cancels out. So it's only 3. Okay? You have 3, 0, and 0. Right? Now, how do you interpret this table? Okay. So epsilon is a small number, right? We said epsilon is a small number, a small real number. When you say epsilon is a small number, so let's say this is 0. Epsilon could be somewhere here, or it could be somewhere here. It could be just a little bit more than 0 or a little bit less than 0. So we have to look at both these options, okay? If first let's start with positive. If epsilon is a positive, a very small positive number, okay? This is positive sign, right? What would this be? So 6 into very small number minus 7, it will be negative, right? And this would be, so if you look at this will actually be positive, because you have negative, very small negative number, much smaller negative number over negative something. So you have big negative over big negative. So this will be positive, right? This is positive. So how many sign changes did you see? 2 sign changes, right? So let's start with, now let's do negative. Okay. If you do negative, this is negative. This would be, why sir? Right. So you have negative, and epsilon would be negative, right? So this would be positive. Similarly, this would be positive, right? Because what will dominate is this -7 will dominate, right? So -7 over -7, that is what will dominate. You have positive. So you have negative, positive, positive, positive. There's one sign change. But what you're going to notice here is, regardless of whether epsilon is approaching from negative or positive, there is at least one sign change. Okay? So what that means? Right. So system is, the number of poles in right half plane is equal to at least 1. Okay? Which implies system is what did we say? System is unstable. If there is even one pole in the right half plane, then the system is unstable. Or if you're looking at Routh-Hurwitz criteria, even if there is one sign change in the first column, system is unstable. And that is all you need to determine for your exam or assignment, okay? The second special case, we'll just wrap it up with the second special case, all right? Case 2. Entire row is 0. Okay. So let's say the example, we'll take a look at example. This is TS is equal to 10 over s to the power of 5 plus 7 is 6, 7, 6. this is given to you. Now again, you do the same thing. You start populating your Routh table, all right? S4 and S5 and S4, S cube, S square, S1, S0. So what are you going to get here? You have 1, 6, and 8, right? And this would be 7, 42, right? And 56, all right? So what is this? It's not negative something, it is 42 minus 42, 0 over 7, doesn't matter. What is this? This is also 0, actually. So you have 56 is what? 7 into 8, right? 7 8s are 56. Right? So you have 6 into 7 into 8. 42 is what? 6 into 7. You have again 6 into 7 into 8. So this minus this would be 0. Okay? So you have, this is also 0. So when you encounter this, you cannot solve using epsilon now. Okay? So you need to look at another way of solving. When an entire row is 0, this is a case 2 or the special case 2. So how do you deal with this? So what you do is you form a polynomial Take a look at this. Okay. What is the polynomial associated with S4? Right, it would be 7 S4 plus 42, just this row. Polynomial associated with this row. 42 S square, right, plus 56. All right. Or what you can do is you can always see, one of the advantages with this Routh criteria is you can, if you see a row, you can simplify if there is a common factor in that. Right? Your answer will not change. For example, you could do something like this. 1, 6, 8. What I did was, the common factor in this 3 is 7. 7 1s are 7, 7 6 are 42, 7 8s are 56. Okay, so accordingly, I can write this polynomial as 6, and this is 8. Okay. And what I do is, this row then would be dps over ds. So what is this? Derivative of ps over s over ds. So the derivative is 4s cube, all right, plus 12s plus 0. So now I use this 4, 12 and keep this as 0. Okay. And I can do again this 1, 3. Alright. So now, again, just do your regular thing. It is, so you have populated this row. What is this now? It is minus 3. What is this? Huh? It's 8, right? Again, it's just this over this. This is 0. What is this? 8 minus 9 over, or sorry, minus 9 minus 9 minus 8 over minus 3. Minus 9 minus 8 is 17 over minus 3. This is 17 over 3. And this would be 0, 0. Alright? And this would be 8, 0, 0. Alright? So, what do you see here? Right. So, whatever row ends up to be 0, all zeros, you go one row up, you form the polynomial. Okay? So, this would be S4, S2, S, or 0, constant. Alright? This cannot be 0. These two cannot be zeros, right? These two. So, it is either this, or this, or this, or this. So if it was this was 0, all right, this row was 0. How would you form the polynomial? You have S3, S1, and 0. All right. So that is how you form your polynomials. So if you look at this again, you have done the route table. You completed the route table. Is the system stable? How many number of poles in right half plane is equal to how much? How many poles are there in the right half plane? Can you take a look at the first column and tell me? Huh? Right. One sign change, another sign change. Okay. So equal to number of poles is 2. Therefore, which implies system is unstable. All right. So this completes chapter 6. I will send out a homework assignment so that you can practice this more. All right. Please give me your attendance. Just write it down here. Right. We might do something similar. Say that again. I actually just noted down your row. All right. So last class we started looking at stability. We looked at basic definitions for stability, and we looked at transfer function, right? If you're given a transfer function, how do you determine if that transfer function is stable or not, or if the transfer function representing the system is stable or not? Okay. Chapter 6, yes. Today we're going to look at something called Routh-Hurwitz criteria, okay, for stability. If you're given a low order system, you can easily determine whether that system is stable or not by going through the poles, right? If you're given a higher order system, you can use this Routh-Hurwitz criteria. Have you heard about Routh-Hurwitz? No? Have Routh-Hurwitz criterion for stability. Okay. So the first thing we're going to do is we're going to take a look at step one is we will take an example and then discuss this. Okay. Example is have this system given let's say you're given this unity feedback system, okay? And you're asked to figure out if the system is stable. this is given, and your question would be, find the system stability. So this, when you're answering, your step 1 would be to generate Routh table. Okay. Routh table for closed loop transfer function. Now this is important. You have to generate the Routh table for closed loop transfer function. Okay. So what is the closed loop transfer function here? The closed loop transfer function is G, let's say T of S is equal to I have 1000 over S cube plus 10 S square plus 31S plus 1 0 through E0. Okay. This is the closed loop transfer function. Is this visible to you guys? Is this visible? Hmm? Right. Hmm? I don't have anything better for now.